Now, our next speaker is Professor Dr. Amy Mueller, and she has a very long description here, but I don't want to take too much time on this introduction, but she has been working on the development of sensors and the data analytics using AI technologies. So, Dr. Mueller.
Thank you. All right, thank you for that introduction. I think just to give you all a sense of where I'm coming from, you can see I have a joint appointment across two departments that both have environmental in their names. So you should, full disclosure, I'm actually on the environmental side of the world, but I started my life in computer science. I moved into environment because I thought I could make a difference there. And I'm definitely transportation curious, so that's why I'm here today. And we'll be talking to you about a project I have with some colleagues in transportation. So I was asked to kind of talk a little bit about machine learning, and my goal for you today is you leave feeling like you can go to conversations where machine learning is being talked about and hold your own, like just not smiling and nodding, like ask some intelligent questions to see if you think people are bullshitting you. Okay, that's our goal for today. So first I want to talk about how in civil and environmental, how should we be thinking about this? This is a valuable tool set. What should we be thinking about? A little bit about the work that I'm doing, connecting the environmental world and the transportation world. And I love that I've been prefaced a little bit in this by other speakers earlier today, and then give you a real world example of how we're actually doing some work like this at Northeastern. Okay, so machine learning, this is kind of where we are. I think that if you take away nothing else from the machine learning world, basically it's us learning from data. So taking lots of examples and learning from them. That is how we all learned to talk and everything else that we have learned. So it's not really a crazy idea, right? And it's interesting, I think I was prefaced in this, because we can use data to help us answer questions where we might not be able to make a physics model of something. Or maybe we can write down the physics model, but it's so computationally intractable that we could never run that physics model on any real data set in any real amount of time. So I think that's why we should all be interested in what capabilities we might have in this space. All right, so how do we get started? This is like the world according to me. We need to actually have a reason we are doing the work. I personally think there is way too much going on in the world where people just say, I applied machine learning to insert random thing here, and then they think it's something new. I'm not sure we learn that much from doing that kind of activity. So starting with a clear goal of what we want to achieve and how data is going to help us to achieve that, I think really gets us farther. And it's really important to think about where those data come from. Do we have them? Do we need to collect them? Do we need them in real time? Do we have the right sensors? The same questions we would ask for literally any other application. It's just that this application is so data hungry that kind of needs to be the first question. All right, and then our second thing is, how do these things all relate? Right? Is that information we're collecting helping towards something that we're trying to answer? And hopefully we were all doing that anyway, right? So we're already winning at this game. And then just the challenge at the bottom is you need a lot of data. And I love this, this order we did this, because like we often need data about the situation we don't want to happen. We most importantly need data about the failure modes. But we don't want to break things to get the data about the failure modes. So that is a real struggle, especially in civil and environmental. Okay, so let's start with something that looks familiar to everybody, right? This is a model we've all seen many times growing up. We all know how to interact with a model like this. It's a straightforward equation. We can stick it in Excel or our favorite modeling tool. We can visualize it. We know the range it applies in. We know if we're sticking an input into it that's way out of where the original data set was, right? It's really obvious. Okay, so if we go to the machine learning world, this is where we are, right? We have no idea what's going on inside the model. There's no equation. There's no clear way to know if you're inside the model bounds, if you're outside the model bounds. And there's no real way to know if your model is going to do something completely crazy if you are outside of the model bounds. So we need to really be extremely careful about the data and about how we think about the data. And I will probably say that 50 times in the next 5 minutes. Okay, so now this is like the 2 slides you all need to take home. So at Friday night parties, you have all of the right vocab. This is the way we all think about modeling, right? We know something about the things we're trying to study. We write down the equations, then we put them in a computer. We do all of our work in that box called the model. We write equations and put it in the box model. We can calibrate our model. We can then use our model. Okay. In the machine learning world, all we have done is change the names of everything to make everything super confusing, but it's all exactly the same stuff. And we have moved to our design happens in this other box. We're not calibrating the model with equations anymore. We're calibrating the model with the data that we use to give it information about the world. This is really the only thing that changes. So we might still know some equations. There's a whole discipline called physics-informed machine learning where we kind of merge the two. But fundamentally, we're just changing our idea about how to build a model from writing equations to giving it data. So again, the data are so important. Okay, so I'm going to talk you through one project that we've been working on at Northeastern to give you like, where did we start from? How did we get there? How are we thinking about where machine learning fits into that example? I'm here talking to you about this because I'm kind of the data and machine learning person on that team. And our goal here was really to think about the connection between transportation systems and air quality, and especially how we could potentially link these more in decision making. So our municipal partners, and honestly the regional planning agencies and other funders of these types of projects are really interested in understanding, ideally ahead of time, but post facto if we need to, are transportation system changes actually having impacts on air quality as well as other things. So we often think about a transportation project, we can model, do we think it's going to increase in congestion? Maybe then we assume it's impacting air quality, but we don't necessarily know by how much. We never measure it afterward because measuring air quality is a little bit difficult. So we kind of set out to answer this question. Could we envision a world where we could bring that as a metric into the conversation? So one of the municipalities that we're working with is Chelsea, Massachusetts. For any of you who have ever been there, you'll know it's a very small city. It's the oldest city in Massachusetts. It's about 2 square miles. They are crisscrossed by literally every single mode of transportation. The airport also has runways that fly overhead. All of the distribution of essentially all fresh fruits, vegetables, road salt, fish, and anything else you can imagine is kind of going through Chelsea out of Logan Airport. And this community is just extremely impacted by transportation. They're also very low on budget because they have a small population and also because their population is in kind of the lower income brackets within the state of Massachusetts. So they don't have a lot of resources. And they're trying to make a case for things like, could we demand that all diesel vehicles be electrified? That would be great, right? But they need a data set to show that. So they were really interested in understanding which of the elements of the transportation system are most impactful, where they should put their advocacy in with the state and potentially looking for federal dollars, and understanding what's even possible in answering this question. So we have a very big team at Northeastern. I'm here representing, there are 15 PIs, about 18 grad students working on this project. It's far more reaching than what I'm going to talk about today. I've highlighted a few folks who are working on the aspects I'm talking about today, who you all might know from other conferences and other activities like this workshop. And this postdoc, Mohammed, and grad student Fatima are the folks who've been actually doing the work that I'm going to show you today, kind of at this connection between transportations and the data science part. Okay, so Horace is actually the person whose group does all of the modeling for the transportation side. And so they started looking at building a Lagrangian model for traffic within the city of Chelsea. So they have some streetlight data. They've essentially built from the ground up a model that they can run for every vehicle in the city for an entire year. And from that, they can simulate emissions. We all know that emissions are not air quality. Emissions become something people actually experience by the shape of the city, the buildings, the wind, everything else that comes into that recipe. And we also know that these models have a bunch of emission factors that are built into them that are very much assumptions. So it's not actually clear how we get around that part. How then in this simulation do we give our municipal partners what they want, which is to understand the air quality impact? What are my citizens experiencing on every street corner, every day, and how is traffic connected to that? So what we've done is actually put up a very extensive network of air quality sensors, and this has been my responsibility, across the entire city to try to measure air quality in as many places as we can, which is harder than it seems like because there actually aren't poles to attach sensors to in all of these places. And then hopefully, that now we have a data set we can match. We have a simulation, we have a sense of where the traffic is. Now we can know air quality at all of these places and correlate them. And hopefully that's where we get insight, right? We had this goal from our partners, from our stakeholders of what we're trying to learn. And so we have about 85 sensors in this 2 square mile city, which is extremely a lot of sensors, but you can still see there are gaps. There are roads in those gaps. So what do we do with that? We need to think now about moving from just these point measurements where the sensors are to estimating what air quality is in all of those other places. And I'll just preface this by saying simple interpolation models are really not helpful in this because you have buildings there. We know that there is really a lot of dynamics in cities. So we're approaching this in a machine learning mindset just on the air quality estimation side. And thinking about how do we fill in those gaps? Okay, so I want you just to like zoom in on this thing I've circled. Those 2 air sensors are a block and a half apart. The coloration here is air quality index, which is without getting into the details, a system that the EPA has developed to hopefully make it easy to understand air quality. And green is good and red is very bad. There are actually 5 gradations in between. And you can see you go from very good to very bad in 1.5 blocks. So if we want to do a good job of estimating what's actually happening with the transportation system and air quality, remembering there's all other kinds of things affecting air quality also, right? We need to understand really how this variability happens. Okay, so we have been working on modeling just that. How does air quality vary over that geographic space in the city using machine learning? And I will not give you any details on this model in the interest of time, but I can talk about it in Q&A for those interested. We're using the information we have from all of the sensors we do have, meteorological information, the building size and height, the road widths, road types. We have lots of information we can use to give us understanding of the system. To understand, okay, if we have a new place and we want to know what's happening with air quality there, now we can predict it. And the way that we sanity check ourselves is similar to building examples in the lab. We have 85 sensors. We only build our model using about 60, 65. We secretly have these other, 15, 20 available. We use the ones that we allow ourselves to train the model, and then we test them against those ones we've held out. So we know the correct answer, and we're testing how well we can get to the correct answer. All right, so how is this doing so far? This is what is actually happening at that sensor where the question mark is over a period of a week. This is how our model's doing. It's not so bad. We're missing a little bit here in the spikes here and there, but so far, we feel like we're doing pretty well. I have not cherry picked the very best. I have not cherry picked the very worst to show you. So we know we still have work to do. We're right now integrating some information that we can get from public models like the Google traffic layer that we can scrape in real time so that we can hopefully get a bit better on the estimates, especially when we have these irregular events, which we all know cities are just a composite of irregular events lined up in time. So the real goal, right, that was my part of this project, is to come back now with that map and lay it over the traffic models so we can do testing. If we can get something passed to convert all diesel vehicles to electric, will that help? How much will that help? If that won't help, are there certain intersections that are causing issues and they should think about timing at those intersections? Are there certain roads that maybe they need to restrict types of vehicles on those roads? Do they need street calming in some places? The goal here is to give our partners kind of policy options and what are the numerical implications of them so that they can start to think about how to invest those city dollars and the time of their staff towards future improvement in their city. Okay, so can we do this? I want you all to feel like, yes, we can totally do this. We have data, we know how to make models. This is just another way of making models, and we need to be careful about it. And this is kind of my opinion about how to be careful about it, is we need to think critically that our data covered not just the great, everything is working fine scenario. We need the failure scenario, or our models won't know how to deal with that. And we need to have a sense of what we want the model to do and really make sure that we match those two things. I think those are my big takeaways. But I think we should always be asking ourselves, should we do this? Even if we can, is it worth doing? If we have a great physics model and it's working, why would we change it? I think that is just silliness, because we trade off a lot of transparency in our models. I think we also have a danger if we have data, but we don't really know the relationship of the data to what we're trying to actually model. So we need to think carefully before we run down this road. And then I think we run down this road. I think that's my opinion. I want to acknowledge there are so many partners who have helped us with this work, because we're essentially using a city as a test bed. We can't do that alone. It's been 30, 40 organizations that have made that possible. And I also want to acknowledge the seed funding for this project that came from Northeastern University, a huge project team. And if you're curious, our air quality data is all streaming directly to the internet at all times. And I think that's the end of my talk.